Okay, so let me first write a problem and try to solve that problem. So, okay, so in the last tutorial, hopefully we have discussed the, yeah, in the last tutorial we have discussed the case where these LP spaces are complete, okay, for 1 less than equals to p less than equals to m infinity. So here we will be discussing one more problem, that LP spaces are separable for the p. So problem number one. So that LP is separable if 1 less than p less than infinity, and that L infinity is not separable. So basically here it is saying that LP space for p from 1 to up to before to infinity, LP spaces are separable, but L infinity is not separable. So we can there is an already proved theorem which says that this is already proved, but here we have to use the fact that without using the proof in the class, without using the proof discussed in the lecture. Okay, so whatever the proof has been done in lecture, we have to prove that L infinity is not separable, but while LP is separable for P not being L infinity and any other space. Okay, so let me first prove that L infinity is separable, and just a minute. So this is the problem. So note that, recall that LP for 1 less than p less than infinity, LP is collection of all sequence such that summation of mod xi to the power p is finite, and L infinity is equals to all sequence such that xi is supremum of xi is finite. Basically, supremum of xi, I belongs to natural number, this is finite. So this is LP and this is L infinity. Okay. So L infinity, why L infinity not separable? Because we can get a bounded sequence which is not just a minute. We have okay. So if you let ei for each subset I of the natural number set n, define define a sequence. So basically one can write it xi, which is at the point I is equals to 1 if I is coming from capital I, 0 if I is not coming from um, I. So therefore if uh, therefore therefore if I and j are two subset of, therefore if I and j are two subset of the natural number set n and they are distinct, that means there's you should have at least one point which is at least in one set and but not in other set, then their corresponding then we should have, we must have not zero, we must have norm of xi minus norm of xj, supremum norm. So norm of xi minus xj is actually equals to 1, because suppose you are taking I is equals to 1 to n, 1 to n, and j is equals to 1 to n plus 1. So that means xj is the sequence which have at the point j, at the point n plus 1 we have 1, and all other point is also 1, but xi at the point n plus 1 that will be 0. So supremum will be supremum of the difference will be 1. So that means uh, you have this difference, this is 1. Okay, now as now consider bi that is equals to, that is equals to um, all those sequence x is in the L infinity such that norm of x minus xi is less than half. Okay, so if you take this sequence, then for each subset I of n, okay, then uh, collection of bi I is in the power set, this is an uncountable collection because this is an uncountable collection, as for I not equals to j, bi intersection bj is empty. Okay, because of this fact, it will have. Okay, because if otherwise if there exists an sequence x is in bi intersection bj, then intersection of xi minus xj, that infinity, that can be written as intersection of xi minus x infinity plus intersection of xj minus x infinity, which is less than 1 by 2 plus 1 by 2 less than 1. That is a contradiction. This is a contradiction. So that says that pi intersection bj is empty. Okay, so this forms an uncountable collection. So therefore, uncountable collection. As why this uncountable collection? Because as the number of, as the power set is uncountable, at the cardinality, as the cardinality of this power set is uncountable. At the cardinality of the power set is uncountable. So this will be um, this will be as the power, the cardinality of the power set is uncountable. So Pn, so this collection will be uncountable. Okay, this collection will be uncountable. Yeah. So So this is an uncountable collection. So therefore Bi such that I belongs to power set of natural number. This forms and collection of uncountable collection of open set forms an uncountable. Therefore, this is an uncountable collection of open sets that uncountable collection of open sets that collection of open sets. This is an uncountable collection of open sets uh, in uncountable collection of disjoint open set, mutually disjoint open set, collection of and when you have an uncountable collection of disjoint open sets, then any sequence in L infinity, any sequence I'm denoting a little differently. So let me give it K. In L infinity, this is the elements. Each fk are here, each fk are element. Here, each fk is an element in L infinity. That means each fk is a sequence. Okay. So intersects fails to intersect at least at most. So okay, this is all. Uncount disjoint non-empty. Basically, this can be okay. I want to prove that this is um, non-separable. Okay, uncountable collection of mutually disjoint non-empty open sets. So there is no countable uncountable collection of non-empty mutually disjoint open sets in L, and that means that says that there is no countable dense subset. That is, there is no countable dense subset in that is there is no countable dense subsets in L infinity that said that L infinity is non-separable. Okay. Now why LP is separable? Because you can consider a sequence C naught now basically. Okay. Now why LP is separable? We will prove we will use the different method. So here for every sequence, for every x belongs to let 1 less than equals to p less than infinity, for every x belongs to LP, okay, for every x equals to xi, I am writing as xn, this is the sequence, is in LP, consider xk is equals to xk is a sequence whose jth coordinate is equals to xj if j is less than or equals to k, 0 if j is greater than k. Then clearly basically here uh, consider C naught is the space of all sequence is the space of all sequence Just a minute. To the sequence with at most only is the space of all sequence with at most finitely many non-zero entries. Then check that C naught node is dense in LP first place, and EI in the sequence of En, which at the point I is equals to delta Nj, okay, delta Ni basically, delta Ni, that is equals to 1 if I equals to n, 0 if I not equals to n. Then the sequence in LP in C naught not is countable dense set in LP norm. Okay. So basically, what we are saying here is that C naught node is dense in LP. How this C naught node is dense, I'll give a little short argument. And C naught node is separable because there is a countable dense set. And what is that countable dense set? That is En, which at the point n is 1 and otherwise it is 0. So why C naught node is countable dense set? Suppose we have an xi. Okay. Suppose we have a sequence xi. Okay. And you want to write p basically. Suppose we have I equals to 1 to, so here I can give, so suppose we are having mod of xi to the power p. We want to I equals to 1 to infinity. This can be written as limit n tends to infinity norm of summation of xi to the power p I equals to 1 to n. Okay, so that means this is equals to limit n tends to infinity. This is the element. If you look at what is that element, what is that element, xk, this xn, this is the element norm of the xn where xn is in C naught naught. Okay, so as xn is in C naught naught, this is not x power n basically, this is the, it's symbolical, this is not x power n, this is in C naught naught. So basically one can, I can give here is the like this bracket type of thing. So this is in C naught naught. So therefore, as this holds, so therefore one can get the, and also this says that summation of I equals to n plus 1 to infinity mod of xi to the power p tends to 0 as n tends to infinity, and this gives that norm of x minus xn norm of pp, which is equals to summation of I equals to n plus 1 to infinity mod of xi to the power, sorry, mod of xin, this is tends to 0 as n tends to infinity. This says that C naught node is dense in LP. And other one is very easy. Okay, so this will complete. This completes this completes the solution of the problem. Okay, so let me go back to another problem. So here it is says let 1 less than p less than infinity and p dash is the conjugate exponent of p, that is 1 by p plus 1 by p dash is equals to 1, so that lp dash is isometrically isomorphic to lp dash. Similarly, without using the proofs discussed in lecture. Proofs. Okay, so here is an important problem that says that let 1 less than equals to p and this is all, and p dash is the conjugate. P dash is the conjugate exponent of p. So then we have to check whether lp dash is. We know that lp dash is actually lp dash is the dual. Okay, this is the basically dual. That is collection of all linear functional on LP. Okay, so this is all. So now we have to prove this one. So let me try to do it. It will be a little long, but so for any sequence, we will be sometimes using the notation xn or xy. So this is standard for any sequence x. We use the standard notation. We use the notation denotes it jth entry. Denotes its jth entry. So basically, we are considering sequencer function on natural number. Okay. So now, for any y, basically yj, basically, okay, yj in L p dash. P dash is the define fy from Lp to complex number c by this fy at the point x is equals to summation of xi yi I equals to 1 to infinity. Then mod of fy x, this is equals to mod of I equals to 1 to infinity x. This is just x, not okay. So this can be written as summation of xi to the power x at the point I. We have taken y from p and x is coming from y from p dash and x is coming from, so this will be p whole to the power 1 by p and summation of I equals to 1 to infinity x y j whole to the power q p dash whole to the power 1 by p dash. So basically this is equals to norm of xp into norm of y p dash. This says that fy is clearly fy is bounded. Sorry, clearly Fy is linear, and the last inequality shows that equality says that Fy is bounded, and norm of Fy as a functional is less than equals to norm of Yp dash for any y is in Lp dash. So therefore, now what we have to prove? Now we will prove that. So that whenever one less than p less than infinity, norm of Fy is equals to norm of Yp dash for y is in Lp dash. So that is, we need to show that need to show that norm of Yp dash is less than equals to norm of Fy. So if we can prove there is a norm attainment, so then we can prove, I think. Okay, but let me try once. So what we can do here? So first of all, take p is equals to infinity. So in that case, in that case, let's consider. So first case, take p is equals to infinity. Sorry, p is equals to 1. P is equals to 1. So that means p dash is equals to infinity. Okay. P can take value 1, but P dash will not take value 1, that we have considered. So therefore, Yj, that is equals to f of Ej. That's clear. If y at the point Ej, okay, where Ej is the sequence the same sequence I have defined few minutes ago in the above. So if we consider Yj is equals to, so note that, so therefore mod of Yj, therefore mod of Yz, which is equals to mod of Fy Ej, which is less than equals to norm of Fy as an operator, and Ej as P norm. Okay, so but that is 1. Okay, this is basically 1. You can check, that's not a big deal. So therefore what we got here actually, that for any j, for any j belongs to natural number, mod of Yj is less than equals to norm of Fy. That says that norm of y infinity is less than equals to norm of Fy. Okay. So therefore, what we got here, we got this one. Therefore the claim is proved, settled. Therefore, claim is proved for p is equals to 1. So conjugate exponent is infinity. Let's take p is strictly less than 1 and strictly less than infinity. Okay. So therefore q will also be strictly less than 1, strictly less than infinity. Take this. Okay. Now, so in this case, if when y is in p dash, then summation of yj, j equals to 1 to n to the power q, we want to show that mod of to the power p dash j equals to 1 to infinity. This is less than is equals to norm of fy to the power p dash. I think this is correct. Okay, this is what we want to prove. Okay, so now note that summation of yj whole to the power p dash j equals to 1 to n, which is equals to summation of j equals to 1 to n f of that is okay, this is equals to x n j f of ej, where f of ej is equals to yj, obvious, this is obvious, and xn is a sequence whose jth entry is equals to yj, its pth dash component by yj if yj is not equals to 0 and j less than equals to n, 0 otherwise. So we have given a new sequence xn, and we will be shortly proving that this xn is a non-attainment point basically. Okay, then clearly xn is in c naught node. Recall that c naught node is the space of all sequence which has at most finite number of non-zero entries. Okay, and from here you can look at and summation of j equals to 1 to n mod of yj p dash is equals to, this can be written as using the in linearity of f. Okay, this is less than or equals to norm of fy into norm of xn p. Okay, also note that mod of xn, its pth norm power p is equals to summation of j equals to 1 to n x n j, its pth power. Okay, which is equals to summation of, this is we had, this equal to we had. Okay, this is from the last, you can say from here. Okay, this is just usual. Okay, this you can replace the value and this will get. Okay, so therefore mm, therefore Clearly the sequence xn is in, this is finite, okay. Clearly the sequence xn converges here I need the sequence where x is converging, that is what we need. If yj is not equals to 0, 0, otherwise then x is in LP, first point, and summation of j equals to 1 to n mod of yj to the power q, that is equals to, and xn converges to x in LP. This you need to check once. So f of xn, which is less than or equals to norm of fy, norm of xp, which is equals to, this is p dash. So norm of y okay, sorry, we got this one right. So yz, okay, we don't need this one basically. We don't need this one. We can avoid this one. Okay, let me. This we have. This p dash is equals to f of xn. This is less than or equals to norm of fy into norm of xn p, which is equals to norm of fy into norm of xn p is equals to j equals to 1 mod of yj to the power q whole to the power 1 by p. That implies summation of j equals to 1 to n mod of yj. So taking limit intensity infinity on both some side, taking limit intensity infinity on both sides, what we get, this will get y p dash which is equals to norm y, this is less than equals to into norm of y p dash by p, that says norm of y p dash 1 minus 1 by p is less than equals to norm of fy. Now recall that 1 by p plus 1 by p dash is equals to 1. So this will says that norm of y p dash is less than equals to norm of fy. So this gives the norm of fy is equals to norm of y p dash. Okay. So therefore For 1 less than p less than infinity, the mass gamma given from LP to LP dashed LP dash to LP, sending every element y to the corresponding linear functional fy on LP is an linear, yeah, is an isometry, is an linear isometry, is an isometry. So we need to show now that this is an isomorphism. So now that gamma is on 2. Okay, this is what we have to show. So now basically what we have to show, for every linear function we have to find. So let if, sorry, this is dashed, let f is in LP dashed, that is a bounded linear functional, that is a bounded linear functional on LP, then their existence y belongs to LP dashed such that f is equals to fy. So what is the natural choice? It is natural to choose natural to choose easy. Then we need to show, then we need to show that y is in LP dash. That first we have to show, right? First we have to show that y is in LP dash, that we have to show. Okay. So for this what we have to do, for any x belongs to LP, f of x is equals to summation of, is equals to, because of the linearity here, linearity and boundedness of the linear function, n infinity 1 summation of j equals to 1 to n xj f of ej, and which we have taken limit n tends to infinity summation of j equals to 1 xj yj. This is we have to taken. So therefore f of yx, that is clear, but we need to show that y is there basically. Y is in LP. How one can prove that y is in LP? So basically what we have to prove, that mod of yi p I equals to 1 to infinity. So also note that sorry, p dashed, this we have to prove, p dashed, oh, that we have from the last one, one can get, yeah, from y dash p dashed one can get this one. So if we can define x like this way, then we will be having and xi is an and xn and xn is in LP, so this is equals to f of xn and this is less than is equals to and so previous the similar argument and similar argument here we can show that norm of f into norm of xn equals to 1 to n xn to the power I to the power p. Okay, this to the power whole to the power 1 by p, then we can do and by similar argument as above, similar arguments as above, as above we get summation of I equals to 1 to n y I mod p dash. This is equals to norm of f for all n belongs to natural number. This implies that norm of yp, I think this will be a p. No, so that says that norm of yp p dash less than is equals to f. This completes the basically. Therefore, gamma is surjective. Therefore, gamma is surjective, and this that is surjective, and consequently, gamma is an isometric isomorphism. That says that this completes the proof actually. The solution of the problem. This completes the solution, the problem. Okay. So now we'll be doing another problem. Okay. So let us find another problem. Okay. So give an example of a continuous linear functional. Give an example of a continuous linear functional on L infinity which does not arise from any element of L1. So basically, here it is asked that so we have seen, note that this is something note type, you can say. We have seen in the last problem, that is problem number 2 of today's session, basically problem 2, that when 1 less than p less than infinity, LP dash is isometrically isomorphic to LP dash. But we have not said anything about that L infinity whenever p is equals to infinity. That means the bounded linear functional on bounded sequence, but this fails for p is equals to infinity. That is, there is a linear functional is a linear functional on L infinity which does not arise from any element of L1. The reason is that in the first problem, that is problem number 1, we have seen that for 1 less than p infinity, LP are separable, but L infinity is not separable. So if just a minute, if also L infinity dash, the question is a continuous linear functional on L infinity which does not arise from mm, if L infinity dash is L1, then L1 is separable L1 dust is L infinity, so that means that will okay. Therefore, by using the below statement, not only prove statement L infinity dash is not isometrical isomorphic to 1, not isomorphic basically. So the statement is that theorem, the dual of a non-separable normed linear space, this is in general space, cannot be homeomorphic so basically let me write it clearly. Dual of a non-separable non-linear space. Non-separable non-linear space. This is in general. We don't need to be normed linear space. Cannot be homeomorphic with a separable space. Okay, the dual of a non-separable non-linear space cannot be homeomorphic to a separable space. Why this is? Because as the dual, so 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 because okay, so I will not prove this. These are the standard you can take from anywhere. A non-linear space is separable. That means it has countable dense subset if its dual is separable. So how it is showing? You can okay. Let me check then. This is let X be a normed linear space. Okay, I will not put this because this is not major theoretic, so I will not put this one. Okay, from this we can say, but these are not theorem. These are the standard theorem from the functional analysis one can use. Okay, so these two are the theorem. Okay, now let me prove one problem, and after that, what it says: let AB be an finite be a finite interval. Let phi k equals to 1 to infinity be an orthonormal sequence sequence in L2 of AB, that is square integrable function. Okay, that is integration AB phi j k phi dm1 is equals to 1 if j is equals to k, if 0 if j not equals to k. Okay, so this is the orthonormality means. Let k equals to 1 to infinity be scalars such that summation k equals to 1 to infinity ck square is finite, so that there exists f belongs to L2AB such that integration a to b f of phi k dm1 is equals to ck for every k belongs to natural number, and secondly norm of f2 square is equals to summation of k is equals to 1 to infinity ck square. Okay, so this is an important theorem that is called Riesz-Fisher theorem. Okay, so here you can note Riesz-Fisher theorem. So basically here it is saying that there is a correspondence from sequence to L2, basically square integrable sequence and square integrable functions, absolutely square integrable sequence and absolutely square integrable function. This is what it is. Okay, so how to prove this one? So here it is given that all pk is an orthonormal basis. Okay, so now consider a function if from AB to, I hope it will be complex value scalars, whatever the scalar it C or R it will be R basically, because here we are in real valued situation. Function FAB, which is given by defined by we have to find the function f of x is equals to summation of k equals to 1 to infinity ck pk x. First of all, we have to check that this sequences converges. This, so basically here this is not this way. Consider a sequence of functions. Consider a sequence of functions fn. So basically what we can write here, fn ax is equals to summation of k equals to 1 to n ck phi kx, then uh, norm of fn minus fm square, which is equals to summation of k equals to 1 to n ck phi kx phi k basically, ck phi k minus whatever the inner product here, it is L2 inner product. So basically, so summation of j equals to 1 to n cj phi j, this norm square, this is equals to summation of k is equals to n plus 1 to n if n greater than is equals to n mod of ck square, because phi k is orthogonal, as phi k are orthogonal. Okay, so one can write it like this way, ck phi k norm square, this is equals to summation of k equals to n plus 1 to infinity, sorry, k equals to n plus 1 to n, summation of j equals to n plus 1 to n, ck cj phi j inner product open interval ab, whatever the dm1, but you do note that these are orthonormal basis, so therefore it will be k equals to n plus 1 to m mod of ck square, whatever the scalar. Okay, so as k equals to 1 to infinity is an orthonormal basis. Okay, so therefore, as summation of ck square is finite, then for given epsilon greater than 0, there exists a natural number n naught, such that for all m and n greater than or equals to n naught, summation of 1 to m mod of all n greater than n greater than whatever it is. Main point is that this is ck square mod is less than epsilon. Okay, so therefore the sequence fn is Cauchy in L2AB, then it converges, then as L2AB is complete, is a complete monospace, complete, then is complete, then Fn converges to the function f given by f of x is equals to summation of ck phi k x k equals to 1 to infinity. Okay, now let me go back to the problems. This is the function created and function is in L2 of AB. Now this, moreover, ck is equals to okay, so basically phi, okay, let me check this one. So let me write this. So moreover, integration a to b f phi k dm1, which is equals to limit n tends to infinity summation of j equals to 1 to n cj phi j phi k integration over dm1. So this is obviously equals to ck, as phi j is an orthonormal basis of L2, whatever it is L2, is an orthonormal basis okay. So first is proved for every k. Moreover, for every k belongs to natural number, we can write this. And norm of f2 square is equals to inner product ff dm1, which is equals to limit n tends to infinity cn whatever it is. Okay, let me summation of n tends to infinity j equals to 1 to n. I'll replace only one value of the function f. Cj integration of pj into f dm1, that we have, that we can write, right? There is no problem writing with this. We just replaced one function value. Okay, but we know this is equals to Cj bar. I think they are not maintaining anything. Scalars is real, so basically this will be mod of Cj square, because this is what it is. Pj f is equals to Cj, that we got in the last one. So this, sorry, summation of Cj square. So this completes the proof. So this completes the proof of the solution of the proof problem. Okay. So let me uh, find another problem. This was the last one, is the problem number 4. So let me get problem number 5. Let a is greater than 0, evaluate integration r to the power minus a x square d m1x. So here we have to use the change of variable formula. So if we consider y is equals to square root of ax, then using change of variable formula, consider y is equals to square root of ax, then using change of variable formula, we get Basically, you can change the variable formula y square. So, and this has a special form, but okay, let me check whether I'm going to discuss why that is going to be square root of pi. Just 1 minute. Okay, so enough to show that. So this is equals to square root of pi by square root of a. So enough to show that. So that integration over r e to the power minus x square dm1x is equals to root of pi. Now by using the change of variable formula, what we got actually, so here the formula is that x1, here we are in the single variable case, so here you don't need to do the change of variable formula. Okay, here you don't need to do anything. Here you don't need to do anything. So basically here we have to consider that x square is equals to u, then 2x dx is equals to du basically. So this will be dx dm1 will be du by 2x, that is equals to du by 2 square root of u. Basically this will be in the change of variable formula, this will be 1 by 2 integration over r e to the power minus u into u to the power minus half, that can be written as e to the power minus half, that can be written as 3 by 2. No, this is all. So this can be written as half minus 1 dm1u. Okay. So this is the gamma function formula. 1 by root 2 gamma of 1 by 2 mm, the gamma function formula, let me check, it is minus 1 gamma function formula. e to the power minus x, x to the power n minus 1, that is gamma n. So this will be gamma half. So what is gamma half? That is square root of pi. But why then 1 by gamma half? As gamma of n is equals to 0 to infinity. Okay, this will be great. Okay, this can be written as due to infinity e to the power minus x, x to the power n minus 1 dx or dm on x. So basically one can write it as 0 to infinity because I'm writing in terms of Lebesgue integral. So this is what it is. So this will prove. Okay, this is what it is. Now let me do the another problem. So this completes the solution basically. So another problem number 4. Sorry, problem number 6. Because last problem was problem number 5. So problem number 6. So what it says, let A be an n times n symmetric and positive definite matrix given a column vector x in Rn, let x transpose denote its transpose so that integration over Rn e to the power minus xt ax dmnx is equals to square root of pi n by determinant of a. Okay, so we'll be recalling something. So as the matrix A is symmetric, so here note that A is the symmetric matrix. So in symmetric and positive matrix, as the given matrix A is symmetric and positive, then there exists eigenvalue, there exists eigenvalue lambda 1 to lambda n with repetition all are 0, all are positive, all are positive, and then orthogonal matrix, and then orthogonal matrix U such that A is equals to U transpose du, where D is actually diagonal of lambda 1 to lambda n. Now we have to find the value of integration over Rn e to the power minus x transpose ax dm1 x. So now if we replace the value e to the power minus x a by this ut dA, so it will be ut dux dm1x. So here we have to do a change of variable. So consider y is equals to ux. This is a variable change. Variable change. So now recall that if we have a variable change, so what will be the matrix? I mean, let me recall the whenever you have the linear operator a, and if you do the variable change, then it will be determinant. I think let me in the statement. Okay, for now we need to if you write this way, integration over Rn e to the power minus y transpose y dm1y. Okay, this you can write with so here note that U being an orthogonal matrix, determinant of U, mod of determinant of U is equals to 1. So that's why that does not affecting anything, but there is a theorem that I want to mention whenever we are doing a change of variable by a matrix. Just a minute. Mm, Where is that? I think I'm not able to recall now, but there was a theorem which uses the fact that if you are doing a transformation, change of measure basically using the matrix. Okay, so this will not affect basically. Main point is this will not affect. So whatever it is this one, and after that we can write it as integration over Rn. So e to the power minus summation of, there is total n number of entries, summation of yi square, basically mod yi square into, here it is lambda I, okay, dm1y, okay. So basically what we can write it as is equals to product of I equals to 1 to n, will be breaking it e to the power minus yi mod square lambda I dm1y. So from the last problem, what we have seen, this is equals to square root of lambda I, and lambda is positive and greater than 0, so square root is possible, into square root of pi. So till now it will be n, till now it will be n, till now it will be n, till now it will be n. Yeah, this is correct. So this is square root of pi by lambda I. So this is equals to square root of pi to the power n into product of lambda I equals to 1 to n, which is equals to determinant of it. So this completes the solution of the problem. This completes the solution of the problem. Okay, so okay, so let me go to the next problem. Problem number 7. Let problem number 7, what it says, just a minute, wait. So take as problem number 7. Let x s mu be a major space and let 1 less than p less than infinity. Okay. Let p dash denote the conjugate exponent of p. So problem is, first, if G is in LP dash mu, define f of x is equals to mod of gx p dash minus 2 gx if gx not equals to 0 and 0 if gx equals to 0. First problem is that so that the way the function is defined, f is in LP. Recall that this way construction we have used in little bit of in the showing in the we are showing that for one less than p less than infinity, the LP spaces are L dual of LP spaces are LQ. Okay, so so first this one. So let me do this mod of FP. P is always from 1 to P to infinity and P dash is its conjugate exponent. Okay, note that if P is equals to mod of G, what is that? Mod of G to the power P dash minus 2 into mod of G, that is equals to mod of G to the power P dash minus 1. Okay, if it is non-zero and all this thing is there, okay, but whenever mm, in this way one need not this say, one should not say this way. Okay, so this is what it is always. Okay, mod of f is equals to this one. If gx is equals to not that if gx equals to 0, then still it is following, and if gx is not equals to 0, still this is hold. Okay, so this is this holds always. Okay, so whether gx is 0 or not, but to define, suppose you know gx, from there to define the function fx, that is little tricky. So that's why this is what it is giving. So you have this one. Okay, then integration over x mod of f p d mu is equals to integration over x mod of g p dash minus 1. But what it is given? G is in LP dash mu. Mm, 'Without finite, how this is going to happen? Okay, note that 1 by p plus 1 by p dash is equals to 1. So 1 by p dash 1 minus 1 by p dash is equals to 1 by p. P dash minus 1 is equals to p dash by p. Yeah, so this is, so integration over x mod of g to the power p dash by p. Okay, so this says that integration over x, what we know, g is in p dash. Okay, so mm, 1 by p plus 1 by p dash is equals to 1. So 1 minus 1 by p dash equals to 1 by p. So p dash minus 1 is equals to p dash by p. Hmm. G is in LP dash. Define this so that f is in LP mu. So this will be in LP mu. Okay. So I made a mistake actually. Yeah. So there is the mistake. Mod of G is equal to, this is what it is. So f is equals to p minus p dash, p dash minus 1, which is equals to, so p dash minus 1 is equals to p dash minus 1 is equals to p dash, which is equals to integration over x mod of g p dash. Okay, d mu x d mu, which is equals to norm of g p dash, this is finite. Okay, so this will be, so therefore f is in LP mu. This is clear. Okay, f is in LP mu. So the second problem, define the continuous linear functional TGF from LP need to real valued. F is equals to this, so integration over x f g d mu. Do you know that for all LP mu, so that TG is equals to norm of G P dash. Okay, so here is clearly norm of TGF is equals to integration over x, sorry, mod of TGF, not mod of TGF is integration over x mod of d mu. This is less than equals to integration x fg mu, and then using the Holder's inequality we will be getting that norm of fp and norm of g p dash using Holder's inequality. So what we get, that norm of tg is less than or equals to norm of gp p dash. So now my point is that to show norm of tg equals to norm of tg dash, norm of tg equals to norm of g p dash, we have to show that there is a norm attainment. So to show the norm attainment, here we will use the technique which I have used for to show the isometry in the first problem of today's session, that we have to construct and sequence function x, sequence of x like this way. We have to construct like this way so that we can use that function. So so we will be constructing a function this type of, like here the way here it is constructed this sequence x and j. So we'll be basically um, try to find the sequence like this basically. Okay, so to try to find a constructed function which is similar to this basically. Okay, so and that is already given in the here in the form of this particular g, this way it is given. So let us construct that function. We'll be considering that function basically. Now if we take, so here we can instead of f we'll be writing h. So now consider if the function given in the part A, the function given in part A, then TJF mod basically mod is equals to integration TJF is equals to integration over x f j d mu, which is equals to integration over x. Recall that f is equals to mod of this, and this is less than is equals to the mod of g to the power p minus 1, so p dash minus 1, so p dash d mu, which is equals to norm of g p dash. Okay. This is norm of g p dash p. Okay. Now also norm of fp, a norm of fp, this is equals to integration over x mod of fp d mu, which is equal to the power 1 by 2, sorry 1 by p. So now if you look at what was the norm of fp, that is norm of g p dash. Okay, this was equals to norm of g p dash I think that was uh, yeah, not p dash by p, basically this will be p dash by p. So if we divide it, so norm of PG mod of PGF by norm of F, which is equals to, it will be norm of G P dash, it will be P minus P dash by P. I think I'm making little mistake. Okay, don't use this one. Mm, Integration norm of FP is equals to norm of P dash. I can use the P dash basically. So forget about this. Norm of FP, P is equals to, so this is the P dash. Okay, so norm of FP, this is equals to, this can be written as norm of GP dash. Okay, P, then mod of PG by norm of FP, which is equals to norm of GP dash, P dash by norm of GP dash, P dash by P, which is equals to norm of GP dash, P dash minus P dash by P, which is equals to norm of, note that P dash, that is 1 basically. Okay, this is P dash. Okay, so therefore norm of TG is equals to norm of G P dash. Okay, so this is the alternative way one can. Therefore this completes the proof of B. Okay, let me show another problem. So to show that for 1 less than p less than infinity, so that for 1 less than p less than infinity, for 1 less than p less than infinity, LP mu reflexive. Okay, using the fact that using the fact that uniform convex Banach space says this is reflexive. That every uniform convex Banach space is reflexive, and a Banach space is called uniform convex if it satisfies some property. What is that property? I'll write that property. Okay, and a Banach space V is uniformly convex if given epsilon greater than 0, there exists delta greater than 0, such that for x and y is in V with norm x is equals to norm y is equals to 1 and x minus y greater than is equals to epsilon, that should imply that norm of x plus y by 2 is less than 1 by delta. So this is the uniform convexness says that for given epsilon greater than 0, there exists delta greater than 0, such that whenever x and y coming from V and norm of x equals to norm of y equals to 1 with norm of x minus y greater than equals to epsilon, then we should have norm of x plus y by 2 less than 1 minus delta. This is called uniform convex. Then the Banach space is called then uniform Banach space. Okay, now we will be using this fact. Hopefully, let me given to uniform convex. Given that every uniform convex also I have to prove that this is reflexive. So to show that reflexive, what we know and what we have to prove. First of all, we have to prove that LP mu is reflexive if reflexive if 2 less than p less than equals less than infinity. Why that is? Okay. To show this, we will show that. Okay, we will not show. First note that this will not show basically. Note that LP is reflexive because if 2 less than p less than infinity, V is equals to LP mu is reflexive Banach space, uniformly reflexive Banach space. There Banach space there is no problem, that I am not talking about. Uniformly reflexive. So prove it. Okay. Next, we will be using this fact that this is a uniformly reflexive Banach space for P, this one. So and also isometric image of also isometric image of reflexive Banach space, reflexive Banach space is again reflexive. Let T from LP dashed mu to LP mu dashed by sending every element to the corresponding TG, which at the point f is equals to integration gf d mu, whatever we are doing till now, and we know this is an isomorphism, this is an isometry, that is norm of Tg is equals to norm of Gp dash. Okay, we know this is the isometry. Then T of Lp dash mu, this is a closed subspace of Lp mu whole dash. Now, if P dash is less than 1 less than 2, that should imply that 2 less than P less than infinity. Okay, so now then by the first statement, we can give it a name. First statement, LP mu is reflexive. That implies LP mu dash is also reflexive. Because we have said one more statement that if the dual is reflexive, then the Banach space has to be reflexive. So LP mu dash is also reflexive. That implies P of LP dash mu being a closed subspace, being a closed subspace is also of a reflexive space. Being a closed subspace of a reflexive space is also reflexive. Is reflexive. That implies LP dash mu is reflexive. Whenever 1 less than P dash less than equals to 2, that implies less than equals to 2, right? 1 less than P less than equals to, that implies LP dash mu is reflexive whenever 1 less than P less than 2, because we are using the fact that the first one is true. We are not proving this one, that the LP spaces are reflexive for 2 less than equals to P less than infinity, by showing that they are uniformly reflexive. And we have said that we have to assume that if a space is uniformly convex Banach space, then it is reflexive. That I am not proving. So except the solution is complete, except the statement The solution is complete. Problem is complete. So this is all. I will stop here, and this is the final tutorial of this course measure and integration of this NPTEL course measure and integration from my end. Thank you everyone. So this is the final session. There will not be any more. There will be no more tutorial or any live tutorial session from my end. Thank you everyone.